what we're going to cover, they're both going to be very good examples of hardware-software interaction and the importance of dividing the work between the hardware and the software in an appropriate way. So we'll look at the trade-offs between a hardware architect and a software designer. Because if you make the trade-off wrong, things may go really bad, as we will see in some of the examples. Okay, I titled this Multiprocessor Caches because the part of the cache lecture that's really left is mostly about multiprocessing, but I'm going to cover whatever we didn't cover in the last lectures. Okay, so you know these. I mean, your readings talk about caches, but they don't go into a lot of detail, so it's you'll follow the lectures more. And I would definitely recommend reading this seminal paper. This is just a 1.5-page paper by Maurice Wilks. Maurice Wilks is a pioneer in computing, clearly. How many of you heard the name Maurice Wilks? Not many, okay. How many of you heard the name Turing? Okay, that's better. John von Neumann? Okay. Not Maurice Wilks? Okay, now you should learn, because we covered multiple ideas from Maurice Wilks. He's really the father of microarchitecture, for example. When we talked about microarchitecture, I gave an example of his paper that really introduced, that was titled basically the best way of designing an automatic calculating machine, right? And also he was the father of caches as well. At least this is the first paper that really treated caches. It's not the first paper on caches, but it's the first paper that really brilliantly described caches. And in the computers that he implemented in the 1960s, he used caches. So I would definitely recommend this paper for you to take a look. And Frank covered part of it, so I'm not going to go into it in detail. So this is what we were covering, basically. We were looking at hardware caches, but the concept of caches are everywhere. Basically, it's in software. Whenever you want to reduce the latency to access to some big data structure, you really want to cache that data structure somewhere. And in hardware, we do that when we access memory, for example. When we access memory, because the memory access latency is too long, we put a piece of memory into a specialized structure called the cache that's fast to access, right? But you can do that in software also, right? For example, if you if you're writing a program that's distributed in a data center, and if you have a huge data set that you're dealing with, like what you're doing with Google, for example, if you're writing a program, and if you want to access some data structure really fast, you bring it to the machine that you're running your program on, right? Your program may be written to actually span many, many machines, thousands of machines, and whenever you're accessing some data, you don't access always some other machine if you need that data. You bring that data into this machine and store it there, cache it, and that machine operates on that data locally. And that's an example of caching. That's in a distributed system, right? And this example happens a lot. That's a different kind of cache you can construct in software. Our focus has been on hardware caches. So hardware caches have the specific structure. You need to have a tag store and a data store. But that's true for any cache also. In a software cache, you always need to first ask the question, does my data structure contain the thing that I'm looking for, right? That's called the tag store, or the index of the cache. And it also has some bookkeeping information that tells you what you should evict from the cache if the cache is full, for example, right? That's one example that we've discussed. And the data store always stores the memory blocks or the data that you really want to cache and have fast access to. Okay, so I wanted to remind you that this structure is in hardware. In hardware, we have specific constraints, but this structure also exists in software. So keep that in mind. You will see this caching many, many times in your life. Okay, so I'll go over some of these quickly because some of these are already covered to jog your memory. Cache performance is really important, of course. If you want to access data quickly, you have a lot of parameters to play with whenever you're designing a cache. Certainly the size of a cache is important. Size of the block that you store in the cache is important. Associativity of a cache, we talked about associative caches, that's important. That reduces your conflict misses if you increase the associativity. Replacement policy is important, and insertion and placement policy, they're all important. Like what do you put into the cache, what do you replace when the cache is full or when the set is full? These are all important, and we covered some of these, right? The cache size, block size, and associativity, how they affect the hit and miss rate. So I'm not going to go into that in detail, but you can refer to the past lecture. So clearly there are many ways of improving cache performance or reducing cache performance, and it's usually a trade-off. There are three fundamental goals that you would like to achieve. You want to reduce the miss rate, so whenever you ask the question to the cache, do you have this block that I'm looking for, you want to get the answer yes, 100% of the time ideally, right? That's hit, that's called a cache hit. If the cache gives you the answer, no, I don't have the block, that's a miss. And you want to minimize the number of cases or fraction of cases where you get the answer, no, I don't have the block in the cache, right? Because your goal in caching is to keep the block as fast accessible as possible. So clearly, reducing miss rate is important, but you should also be careful because not all blocks are equally important from a processor's perspective, or from because some block may be very important. Because if you actually need to refetch the block, you may actually need to pay a lot of penalty costs. So some blocks are more important than others. We didn't go into this a lot of detail, but keep that in mind. Why? Because the block may be longer to access, or the block may be actually important because it may actually lead to a lot of other accesses, a huge dependency chain that may enable a lot of computation, whereas some other block may not be that important because it may actually be used by a single instruction, and that instruction is not that important in the grand scheme of things. So one example of this is a branch instruction, for example, a branch instruction that checks a value in a memory location. Of course, you need a load instruction to load it, and then the branch instruction to branch on it. If that branch instruction is correctly predicted, maybe that block is not that important, right? So, of course, you need to imagine different cases where that's also, if you need to wait for that branch to resolve for a long time, of course, that's not a good idea. But if your instruction, if you have only one instruction that's dependent on a cache block, and that instruction is already executed nicely in some way, you just need to verify it, maybe that cache block is not as important. Whereas another cache block that leads to the execution of 10,000 instructions, because it's the beginning of a dependency chain, that cache block may be more important. Right? So it's important to consider this also. It's not just about the miss rate, it's about the cost of a miss. Which block is more costly, which block is more important? We didn't go into this, so keep that in mind. In real life, you need to take this into account. Okay, so reducing miss latency or miss cost, that's important. I gave you an example of this. Some misses are more costly than others. And reducing hit latency or hit cost is also important, right? Because whenever you hit in the cache, you don't want to wait 100 cycles for the cache to give you the answer, yes, I have the block, or I don't have the block, right? You want the cache to give you the answer very quickly. One cycle ideally, especially if the cache is in your processor, if it's an L1 cache, ideally you would like to get that answer in one cycle. But unfortunately, if you want to optimize all of these together, it's really a trade-off. Because if you want to reduce hit latency, for example, you want to make the cache smaller. And if you make the cache smaller, it's likely that your miss rate is not going to be very low, right? And so there's a fundamental trade-off between these different parameters. And when you include cost inside the optimization target, it becomes even harder because cost has a lot of different aspects associated with it. One aspect I gave you, how long it takes to fetch the block again. Some blocks, for example, some blocks, you can fetch them from the next level of the hierarchy in 10 cycles. Some other blocks may take 1,000 cycles because they may reside in some other node, some other machine, let's say. Or they may reside in the disk, not necessarily in the next level of the cache. So that's the difference between the latency, different between the missed latency of different blocks. And miss cost we've already discussed. Okay, I'm not going to go into the detail, but you can imagine that this is a complex optimization problem that people are still trying to solve. Caches have been around for more than 50 years, almost 60 years now, and people are still figuring out how to do the caching much more efficiently, because it's so important for performance, right? You don't want to pay the penalty for going into the memory. Okay, so as a result, people have developed many techniques to improve cache performance. We didn't cover the gray ones over here. We were covering the software approaches. I'm going to finish the software approaches and talk a little bit more about other stuff in caches. So you don't need to worry about the gray ones, but recall that these are all ideas that have been implemented or proposed that are employed in processors to make the caches better. And if you're really interested, you can search for them, but we're not going to look into that in this course. Let's talk about the software approaches, because caches are there, and people have tried to take advantage of them in software by doing many things. So this is something that we talked about in the last lecture. I'll go through it quickly. I'll give you examples of the data access patterns, which Frank talked about, but I'm going to focus more on the data layout later on. So if you have a cache, you can take advantage of it by writing code that's friendly for the cache, meaning that your access patterns in the code is good for caching, so that you maximize the hit rate, for example, or you can choose to do otherwise and not take advantage of the cache, right? Or you can, and you can also structure your data such that it's friendly for the cache. You maximize the hit rate. Okay, so there are two directions, basically. Restructure the data access patterns, restructuring the data layout. Let's talk about the data access patterns. Basically, you can do both, restructure data layout or data access patterns. And in this case, I'm going to restructure the data access patterns. I'm going to give an example of the layout. So maybe we should go through this quickly, because I think Frank went over it, but I'll give you a very quick example of how I like to think about this. Let's go to the DocuCam. So we have, before we go to the DocuCam, let's take a look at this. Basically, in this case, assume that you're going over a matrix, a two-dimensional matrix, and somehow your data was laid out in a column major manner. Column major means the single column that you have is consecutive in memory. And if you actually write code that touches different columns, this is not good for caching, because your cache, the data is laid out in such a way that a single column is consecutive in memory. And whenever you bring a block, you're really bringing a single column, not a row. So let's take a look at this example over here very quickly. I'll pick this red one. Okay, that's the DocuCam. So basically, we have this matrix. Well, you can see it. And these are the rows, 0 and -1, let's say. And these are the columns, 0 and -1. So a column major means that this column is laid out consecutively in memory. So if this is an address 0, this is an address 1, address 2, address 3, address 4, ... And so whenever you're actually touching some data over here, you'll bring the block, a cache block worth of data into your cache. And if it's column major, if it's laid out this way, you'll really bring the entire column. So if you really want to take advantage of your cache, the way you would like to traverse your data structure is really this way, right? You want to traverse the entire column, because whenever you touch this element, the entire block will be brought into the cache, and you will make use of the block in the next access, next access, next access, next access, next access. That's the idea over here. So if you go back to this code over here, so if you actually do the other thing, do the opposite, if your data is laid out this way, and if you actually touch this one in the code, and then this one next, 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 it's really bad, because this came into your cache, but you're not taking advantage of it. You're touching this one next, which is bringing a different cache block, but you're not taking advantage of that cache block either, because you're touching this one next, which is bringing a different cache block. Again, you're not taking advantage of that cache block. You're touching the next cache block over here, so you're getting cache misses. If you traverse the matrix this way, then you'll get cache misses in all of the accesses to different columns over here, because your matrix is laid out in column major order. Make sense? So you don't want to do it that way. And this poor code over here, unfortunately, does it that way. So if your matrix is column major, you don't want to write code like this that goes through the columns, because you'll get cache misses in every access. So how do you fix this problem? There are two ways of fixing the problem. If you want to traverse the array, traverse the matrix this way. One way is restructuring your access patterns. So you will realize that at least in this particular example, you're basically summing up all the elements, it's better to go through the rows first, because that gives you an access pattern down the column, right? You access this row first, this element first, and then this element next, and this element next, and this element next, this element next, this element next. So the first access is a miss, but all of the other ones will be hits because the cache block contains all of that data. So that's one solution to the problem, and that's the restructuring of the access pattern by doing this loop interchange. You basically change the order of the loops this way. So that's a better code. So hopefully you minimize the cache miss rate this way. I mean, there's another solution to this problem, of course, right? If you actually are doing this all the time, if you actually have this code, you can also change the layout of the data. You can change the layout to be row major, such that row major means that address 0 is here, address 1 is here, address 2 is here, ... And then address n is here, n plus 1 is here. So if you're actually traversing this way, which was the pru code before, if you change the layout of your data to be this way, then you will still get a very good hit rate in this case, because you're taking advantage of the fact that you're bringing a cache line and you're actually accessing the elements in the cache. Okay? So hopefully this is now obvious. It's surprisingly obvious, but there's a lot of code out there that actually doesn't take this into account. And this makes a huge difference, actually. And in this example, this particular optimization is called loop interchange. Existing compilers, if they realize this, they actually also are able to do this. So compilers are also able to change the access patterns with some complexity, of course. There are other optimizations, of course. You can merge arrays, for example. You can do fusion of the loops, so you don't need to worry about that. But there are many other optimizations that people have developed to increase the cache hit rate. So another way of increasing the cache hit rate is somehow dividing the loops operating on arrays into computation chunks so that each chunk can hold its data in the cache. So basically, the idea is very simple. Essentially, divide the working set so that each piece fits in the cache. So let's see, this is also called tiling. Let me take a look at that very quickly also with this sort of example. I'll give you a high-level example. So if, for example, you have this huge matrix, and let's assume that you're multiplying two matrices. And let's assume that your cache, let's say that this is, I'll do it pictorially, I think. Basically, this is the size of your matrices, but your cache can only store maybe 1/4 of this matrix and 1/4 of this matrix at most. If you actually go through both of these and try to store both of them in the cache, meaning that access the entire matrix, entire matrices at a given time, then you will really overwhelm your cache because you'll get a lot of cache misses. Alternatively, what people have found out is that you can change the way you do matrix multiplication such that you don't do the multiplication of this entire row and this entire column, and then go to the next row, and the next column, and the next row, and next column. That's normally how you would do the multiplication, right? But people have found out that if your cache is too small to house both of these matrices, well, divide your matrices into smaller chunks, called tiles, let's say, and then do the mini multiplication with these chunks, right? Okay. Now, if you do this, the hope is that both of these will be in the cache, and you'll get a lot of reuse whenever you actually do the multiplication of this row and these different columns, and the next row and these different columns, and the next row and these different columns, right? This way, you're fitting everything into your cache, hopefully. Of course, I gave you a high-level example. You need to optimize the code. And then you can store the intermediate values, and you can do the multiplication of this one with this part, right? Now, this is in your cache. This is not needed anymore, perhaps. And you will fetch this part into your cache and do the multiplication, right, of these rows. So this way, this is by tiling the matrices this way, you minimize the cache miss rate because you're not overwhelming the cache with these huge matrices, but you're really dividing your working set such that you're operating on amount of data that can fit into your cache at any given time. So the hope is that this 1/4 and this 1/4 together fits into your cache, so you get very good cache locality. And then when you move from this 1/4 to this 1/4, this is already in your cache, and this will fit in your cache, you get very good cache locality. Make sense? And then you can move in some way. So of course, there are different traversal methods to maximize the cache hit rate in this case, and people have optimized this a lot also for matrix multiplication. So if you're doing matrix multiplication, or if you're doing any sort of traversal in an array, you would like to divide your working set such that whenever you're operating on some data, that working set fits into the cache. Okay, so hopefully that's also obvious. This is also called tiling or blocking, and you will see both terms. And if you're actually using, for example, matrix multiplication a lot, usually you use libraries, and library codes are optimized to do this tiling. But of course, they need to know the cache size. So clearly, if you would like to do this sort of optimization, you need to know the cache size. You also need to perhaps know the associativity as well, right? Depending on what you're really doing with the code. Okay, so let's take a look at another example. This is a restructuring data layout. So if I give you this code over here, what this code is doing is you have this structure, like basically you can look up people based on some key, perhaps. You have some student ID maybe, and this is a pointer-based data structure. It's a linked list in this case. Assume there is a huge linked list, like 1 billion nodes. And in this case, we're traversing the data structure starting from the beginning node, and we're checking if a key exists. So we input a key, and we're checking if the node is if the key of the node is equal to the input key. So it could be student ID, let's say, right? Or it could be ID of a person. And if they're equal, then you access the name and the school, and you maybe print it out. Otherwise, you go to the next structure, next node in the linked list. Does anybody see a problem with this in terms of caching? Yes? Yes?
Depending on the size, couldn't it be that you're always accessing a new block and then you always have to fetch a new one? Exactly.
And you know the size here, right? Which is, in this case at least, it's a C syntax. The size of the name is 256 bytes, and the size of the school is 256 bytes. So the way, if you write this code, you will certainly get a very poor cache hit rate, very poor performance. Why? Because this data structure is laid out in memory in a sequential manner. What you're doing is you're accessing next and key, next, so okay, let me give you, I guess we'll switch to this over here. So if you look at the data structure, it has next, probably 4 bytes. It could be 8 bytes also. It has key, 4 bytes, let's say. And it has huge 2 fields. This is 256 bytes, not to scale, name, and school. So this is what the data structure looks like. And this next pointer points to another one of these. And this next pointer points to another one of these. They don't have to be consecutive, but they can be. In fact, let's assume that they're somehow consecutive. But the point is that this is 520 bytes, right? And if your cache block is 64 bytes, what's happening is you're really accessing next, and if the key doesn't match, you need to access this other next over here. So if this is address 0 and this is address 519, this is at address 520, and add 519 more, 1039, right? And then add 519, this is 1040, and this is 1560 over here, right? I hope I did that right. Okay, so assume that these are the memory addresses. What you're doing is really you're getting 0 cache locality because you're touching next and key in each access. And likely it's not going to match because you have 1 billion nodes and unique keys. So you're going to go to the next one. You're going to touch next and key. and you'll get a cache miss over here because the cache block that you brought in, when you touch next, is going to contain essentially this part, right? And then you'll go to another cache block. That cache block will contain essentially this part. You'll go to another cache block. That cache block will contain essentially this part. So it sounds terrible, right? Because we didn't do the data structure layout nicely, because essentially, even though these fields are not frequently accessed, and we expect them not to be frequently accessed in a code like this, right? Because you're really searching for a key, and if the key is unique, even if it's not unique, well, there could be other issues if it's not unique, but if the key is unique, then you really are going to traverse a lot of nodes before you get to the node where you really need to access name and school, right? So the problem is really other fields, or name and school in this case, occupy most of the cache line, even though they're rarely accessed. And rarely accessed is here, when the key matches. So how can you fix this problem? Yes?
Maybe the key set.
Say it again?
Just have a set of containing all the keys, and you just check the keys in there.
Exactly. Exactly, so that's the solution. This is one way of doing the solution in C. It may not be the best way, but it's an example way. Basically what this does is it puts the keys and the next in the same data structure, such that you don't need to bring in this huge amount of data into the cache whenever you access the key and next. But I think his solution is also valid. Basically, you have a key set somehow, and then you go, it depends on the data structure and how much dynamically you update it, how you actually solve the problem clearly. Okay, so hopefully that's clear. Well, actually, I'll give you the example of basically why this works very quickly. Essentially, what this does is, now our data structure is much simpler. You have next, key, and then pointer to this huge thing for name and data, name and school, essentially. And then in consecutive things, you have the next, key, and the pointer. And then in the next consecutive one, you have the next, key, and pointer. And then you can imagine the rest. Now, whenever you access the first one, you get 64 bytes, which can really fit a lot of these things over here, right? That way you get much better cache locality, because you're not wasting your cache space with things that you're likely not going to touch by restructuring your data layout. Okay. So the idea here is we separate the frequently used fields of a data structure and pack them into a separate data structure. Right? That's what you meant by key set, for example. You pack the keys in a separate data structure. So the question is, who should do this? Right? Clearly, there are many, again, since you're taking this course, you can imagine many places where this could be done. The programmer could do this. That's true. And as good programmers, you should probably do this. The compiler can potentially do this. The compiler can figure out which parts of the program data are frequently accessed. It can restructure the data layout of the program such that frequently accessed parts are put together in the memory layout, such that whenever you access a part, you'll get a frequently accessed part next to it. So the question, of course, this is difficult for the compiler, because compiler needs to know the access patterns now. But actually, aggressive compilers do this sort of optimization. Can the hardware do this? That's a good question. It may not be very easy, because restructuring the data layout internally is possible in hardware, but there are a lot of proposals where you could also do this in hardware too. So clearly, the burden, if you put the burden on the program, it's difficult to do. If you put the burden on the hardware, it's difficult to design the hardware. And this it's an example of a programmer microarchitect trade-off again, right? Again, I'm not going into the details of how the hardware could do it, but you can imagine that the hardware will be complex to be able to do this. It's not just the caches, it's also which parts of a cache block are frequently accessed. You're trying to figure that out. And people have proposed solutions to this, and some of the existing processors actually employ those solutions. Okay, so who can determine what is frequently used? That's a key question. Sometimes the programmer can do a good job, because the programmer knows the access patterns and knows how the data may be, but sometimes they may not be able to, right? Especially in a fine-grained manner, they may not be able to. Okay, So let's switch gears a little bit. There are a lot of other optimizations, software and hardware-based cache optimizations that we can talk about. Actually, the major conference that we have in computer architecture is called International Symposium on Computer Architecture. Many people used to joke that it should be called International Symposium on Cache Architecture, ISCA, right? Because there were so many cache papers that appeared, and they're still appearing actually for a good reason, because caches are everywhere and we need to utilize them better. But I'm not going to talk about that. If you're really interested, you can take the advanced courses in computer architecture. But I'm going to talk about a couple of issues related to multiprocessors in caching. I think these are fascinating. Again, we're not going to go into a whole lot of detail in these topics. This is mainly to make you aware that these issues exist and they require solutions. And there are solutions, but they're not necessarily enough. So if you look at a multi-core system, it has a lot of caches actually. This is an old multi-core system where cores are big. Right now, cores are actually smaller. So even the core has actually caches. So a lot of the parts of the core is caches here. L1 cache is not shown here. There are L2 caches. There's a shared L3 cache in this example. This AMD Barcelona from 2006, it's old. So cache efficiency actually becomes even more important in a multi-core system, in a multi-threaded system where multiple applications or threads are actually sharing the cache. Why? Because memory bandwidth is at premium. You don't want all of those memory accesses to go to memory because memory bandwidth is a big bottleneck. And cache space is also limited across those cores. Imagine you have a 32 megabyte cache and you have 40 cores. If you divide 32 by 40, you get less than 1 megabyte on average for each core, right? And that's very small actually. So the key question people have been looking at is how do we design the cache in a multi-core system? And there are many decisions that are to be made here. Do you make the caches shared versus private across the cores or across the threads? We're going to look into that. How do you maximize the performance of the entire system if you actually have this sort of optimization problem? How do you provide quality of service to different threads? Because when different cores are sharing the cache, how do you ensure that one of them doesn't destroy the performance of another? I'll give you an example here, but we're not going to talk about a lot of solutions. You may imagine some solutions. Should the cache management algorithms be aware of threads? So far we've discussed replacement policies, for example, and we didn't say this replacement policy considers multiple different cores or multiple different applications. We said something else, right? If you have multiple different applications sharing the cache, you really want to design a replacement policy that's different from what we've discussed. LRU is not a good solution, actually. LRU is a terrible solution. Even random replacement is not a good solution in that case. So you should really be aware of the threads, actually. And how should the cache space be allocated to threads in a shared cache? I'm not going to answer all of these questions. I'm going to cover a couple of interesting design choices. So this is one. In this case, I'm assuming L1 caches are private to the core. But if you are multi-threading in a core, even L1 caches are shared between different threads inside a core, actually. That's true for GPUs, for example, very heavily. So what is private cache? Private cache means that cache belongs to one core. A shared block can be in multiple caches. So this is an example of a private cache. This L2 cache is this core's cache. This L2 cache is this core 1's cache. This L2 cache is core 2's cache. They're all separate. So a shared cache, on the other hand, cache is shared by multiple cores. So in this case, for example, if both cores require access to a data element at address A, that address A gets replicated in the two caches. So that's one issue. Shared data is actually replicated. In this case, shared data actually has only one copy. So there's one advantage. So there are a bunch of advantages and disadvantages to these designs. I'm going to step back at a higher level. So this is really an example of resource sharing, right? In this case, you have a private cache. In this case, you have a shared cache. This is your private resource, your shared resource, right? So what is the idea? What is the general idea? Instead of dedicating a hardware resource to a single hardware context, allow multiple hardware contexts to use that resource. And caches are one example of the resource, but this resource could be functional units, pipeline. We've seen pipeline, right? You don't dedicate the entire pipeline to a single thread, but you do fine-grained multi-threading on it. So that's an example of a shared resource also. But this is true for buses and memory as well. So why would you want to do it? This is good because this is how you can really maximize utilization or efficiency. Because whenever you dedicate a resource to a thread, if that thread doesn't use it, it gets wasted, right? You have all the space dedicated for a 4 megabyte cache for this particular core or thread, and that thread is not using it. Too bad. No one else can use it now because you've dedicated it. But whereas if you shared it, you would improve the utilization and efficiency. You get higher throughput because whenever the resource is not used, some other thread can use it. And also there's another advantage. If you share, there's no need to replicate the shared data. If threads access the same data, you don't need to replicate it. This reduces communication latency also because if you have data that's shared between multiple threads, it can be kept in the same cache when those multiple threads access it, right? The data doesn't need to move from cache to cache. This is going to be even more interesting when we talk about cache coherence in a little bit. And also, if you're doing shared memory programming, which you've seen in some other courses, or you will see, this is compatible with that shared memory programming model. In shared memory programming model, each thread can access a memory location, right? They can say, I would like to access memory location A, and that location A is true for all threads. Okay, so there's of course a downside with resource sharing as well. Basically, it leads to contention for resources. Whenever the resource is not idle, another thread now cannot use it. Basically, a thread conflict or contend with each other, right? So the contention can happen in space or time. If the space is occupied by one thread, another thread that needs to reoccupy it. So if you have a cache and you need to access this particular set, and the set has blocks that are brought in by some other thread or some other core, well, too bad. You need to kick them out and then take that space. And now the other core whose blocks you kicked out, now it needs the blocks again. What does it do? It kicks your blocks out, right? So you have this contention for space, essentially perpetually if you have bad access patterns. This is similar to basically sharing a seat, right? You have a seat over here, but that's the only one seat, and only one person can occupy it at a given time. But if that's the only seat that's inside this room, everybody will be contending for that seat, right? Okay. So this leads to, of course, reduction in performance. Each thread's performance reduces, or some threads' performance reduces. And thread performance actually can be worse than when it's run alone. Imagine a case when you're running this thread alone with a 1 megabyte cache, and that thread is using the cache nicely. It gets a lot of locality, no misses in the cache. Now you put another program. Okay, let's say you have two programs. Both of them, when you run them alone, they get 0% miss rate in the cache. Ignore the compulsory misses to populate the cache initially. They both fit in the 1 megabyte cache almost perfectly because the cache is 1 megabyte and they're both occupying the 1 megabyte. Now, if you put them together and both of them have a working set of 1 megabyte and your cache is still 1 megabyte, now you may actually get 0% cache hit rate in that case. It could actually be really bad because these two programs contend with each other and both of them together thrash the cache. This is an example of cache thrashing. So you may not actually want to run them together sometimes. So this is an example of also performance isolation. You get inconsistent performance across different runs of a program. So you run the program once, because it's running with a nice program next to it, you get very good performance. You run the program again, it may run with a very heavy program that basically floods the cache. And then you get terrible performance. Now you have no performance isolation, right? And performance isolation is important for quality of service. Like whenever I want to get a response from my phone, I want some latency guarantees, right? But if the thread that's actually responding to me is getting trashed in the cache because some other program is destroying its cache locality, then there's a problem, right? So these are real problems with resource sharing. And essentially, thread performance depends on other threads that are co-executing with this thread. And if you have uncontrolled sharing of the cache, this leads to quality of service issues. So you need to control this problem, actually, because otherwise you cause a lot of unfairness and starvation. And again, I'm not going to go into the details, but you can construct cases very easily, as I just described. So you have a need for efficient and fair utilization of shared resources if you're actually resource sharing. So let's go back to private and shared caches a little bit and talk about the advantages and disadvantages. So I'm going to talk about the advantage of shared caches, first of all. I've given you a bunch of these already. So if you have a shared cache, you get high effective capacity, right? You have, as opposed to having 4 1 megabyte caches, you have a single 4 megabyte cache. If you have 4 1 megabyte caches, and if you're running 4 programs, and one program needs 3.5 megabytes, that program will not get good performance out of the cache. And all of the other programs may need only 5 bytes, right? And they're not utilizing their cache well. But if you have a 4 megabyte shared cache, all of them fit in the cache, and they work perfectly, right? So that's the beauty of sharing high effective capacity. Under those conditions, everybody gets happy, right? So this is an example of dynamic partitioning of cache space, of course, right? This way, you don't get fragmentation due to static partitioning. If you statically partition the resource into 4 1 megabyte chunks, the applications that are using that need more cache don't get more cache. The applications that don't need the cache cannot give away the cache, so you have a problem. So, and that's the idea of fragmentation, basically. You really fragment the resources if you don't partition them dynamically. And I've already said this, so I'm not going to go through this in detail. So it turns out with shared cache, it's easier to maintain coherence, and we're going to talk about coherence in a little bit. A cache block is in a single location. So whenever someone updates that cache block, everybody else sees that update. Okay, so disadvantage, unfortunately, if you have a large shared cache, you get slower access because you cannot couple the cache with the core. So in this picture over here, this is a lot faster to design because you just need to have access to from this core to this cache. Whereas this is a bit harder to design because all of the cores need to be able to access all of the cache. And as a result, you have a more complicated interconnect and more complicated cache controller. It's not shown here clearly, but you can guess that that's the case over here, right? You have 4 things that are accessing the single cache over here, whereas you have only one thing that's accessing the cache over here. Okay. And clearly, whenever you have a shared cache, cores can incur conflict misses due to other cores' access, and we've seen this. I've already discussed this before. Some cores can destroy the hit rates of some other cores. Again, you may actually have a 4 megabyte cache that's shared between 2 cores. If one core or one application is running alone on that, it may be accessing only 100 bytes. And 100 bytes is good enough for it to access, and it gets great cache locality. It always sits in the cache on those 100 bytes. Now, if you put another application to share that 4 megabyte cache, if this application is very memory intensive, if it doesn't have very good cache locality, let's say, if it keeps on streaming and accessing billions and billions of bytes, the other application that just needs those 100 bytes may not actually get the cache space for those 100 bytes, and it could keep getting cache misses, right? If you don't control the sharing. So it could actually, this interference between the cores actually can lead to this destruction of performance for even applications that are very good cache locality, that need very little cache space. So okay, basically guaranteeing a minimum level of service to each core becomes harder because now you need to basically decide how much space and how much bandwidth you allocate. So this is one example. This is from one of the earlier papers that talked about some of these problems. Basically, the problem looks like this. You're running this blue thread in a shared cache. If that blue thread is running alone, it needs this much space, let's say. Now, if you run this other thread, T2 over here, this orange thread, it needs this much space. Now, whenever these 2 threads run together, for some reason, this blue thread gets the space it needs, but the orange thread doesn't get the space it needs. This could happen because this may have access patterns that are more intensive, right? That's kicking out the orange threads block. It could actually be even worse. This orange thread may not really exist as much in this shared cache. As a result, you may actually get this orange thread's performance destroyed. Again, existing processors have ways of solving it, not necessarily the best ways. So for example, you could actually partition the caches across different threads, across different cores in Intel processors or ARM processors today. But that requires some control from the programmer. So people have proposed doing this dynamically. Hardware provides mechanisms to actually do this partitioning across the threads. I'm not going to go into those in detail. There's a lot of fascinating research that goes on in this area. And this problem is even worse because caches are everywhere. So it's you may think this is not necessarily a problem with the shared L2 cache. It could be a problem with the shared L3 cache. It could be a problem with shared memory, as we will discuss in a little bit. But also, what complicates the problem is, usually in today's systems, you don't have a monolithic cache. What happens is, caches are distributed across the chip. So you have this core, and a slice of the L2 cache is actually close to this core. You have another core, another slice of the L2 cache is here. Now, this is logically the same cache, but physically it's distributed across the core. And now you still need to ensure that you get good performance in a system like this. Again, I'm not going to go into detail over here. This is just to show you an example of the wealth of problems. In essence, what you have on a chip is a distributed system on a chip. You have distributed cores, and you have distributed data, distributed storage, where you can store the data, and they're called caches. And you have some interconnects connecting them. And you have other distributed storage that looks like this. This is, of course, a cartoonish picture, but many chips actually look this way if you blink a little bit. So essentially, most of the memory system is a shared resource storing and moving data. How to actually partition it across different threads is a problem. So you don't want to run into situations like this, basically. If this application's performance is really important, you don't want its performance to be destroyed by this one. Okay, so I think this is a good place to take a break. We'll start with cache coherence, and we'll hopefully finish with virtual memory. Okay, let's continue. Whoa. So recall that we finished with this picture over here. And once you look at this picture, you can imagine many problems, actually. This is many design choices. Because as I said, you essentially have a distributed system on a chip. And there are many really interesting issues on designing this distributed system on a chip. And clearly, there are many interesting issues on designing this part as well, right? The memory and the storage. But we're not going to go into that because we don't have time. But I will introduce one problem that's one of the interesting and important problems, and it's the cache coherence problem. It's very fundamental. Whenever you have multiple different threads or cores accessing memory, you run into issues with shared data. So the basic question is very simple. If you have multiple processors, like this, P1 and P2, and if you have different caches associated with those processors, and if they cache the same block, same cache block, assume that this block X, how do you ensure that they all get the correct data? They all see a consistent state, in other words, or coherent state. Consistency and coherence, I'm using them in the same way in this particular case. So we have this X1000 that's originally in memory. Actually, originally it's in disk. It gets into memory somehow. And then later on, processor 2 loads it into, basically it wants to load from address X. When it wants to load from address X into a register, the cache block gets fetched from memory to its cache. And now it's 1,000 over here. Okay, so far so good. That's how caching works, right? Now, processor 1 is loading the same block. It could be shared data. They could be accessing some shared data structure. It could be a lock protecting a data structure, right? Because if you're doing shared memory programming, how many of you know about locks? Okay, good. So you've done shared memory programming, most of you. So it could be a lock so that you can test the lock, right? So that's another example of shared data. It's a shared lock. Now this processor also loads X to register 2, okay? And it gets the value 1,000. So far, so good. Everything is consistent, right? Now, let's take a look at an example. This processor does something and stores, basically does something to value X, and then stores X into the cache. So let's assume that this resulted in the value of the block to be 2,000. Now it stores into the cache, and assuming the cache is not a write-through cache, this is the state that you would get. In this case, the value of X is updated in this cache, but it's not updated in this cache, it's not updated in memory. Now you have an inconsistent state, which may not be a problem if no one else touches this block, and later you propagate this. But if this processor 2 now loads X again, the question is, what should it get? Well, it should not load 1,000 because now you have an inconsistent state, right? And that's the cache coherence problem, basically. Because you have multiple caches and the same data is replicated across those caches as well as main memory, you have a consistency problem. You need to make sure that data is coherent or consistent across all of the caches. Now, what if it loads 1,000? So what if this was a lock? So if this was a lock and you needed this core updates the lock, indicating that it has the lock right now. If this processor loads 1,000, it will think, okay, nobody else has the lock, so I can access all of the shared data myself, right? So that's the problem over here. You can actually get completely incorrect results because this is not expected, this is not visible to the programmer, these caches. So who should fix this problem? Basically, for this to work correctly, what should happen? I guess you could ask the question, right? Whenever this processor writes to this location, you could imagine that that write also goes to here and also goes to here. That would fix the problem, right? That's one way of fixing the problem. Whenever a processor writes to a cache block, every other processor that has that cache block gets the same value that this processor is writing, and also a main memory. If everybody has 2000 over here, the problem is solved. That's good. Or another solution is, whenever this processor writes to a cache block, you send a message to all of the other caches saying, I'm writing to this cache block, just get rid of the old value that you have. So another solution would be, whenever this writes, this processor gets rid of the cache block. So it doesn't even cache this block anymore. It invalidates the cache block. And memory is also, you cannot invalidate memory, so you need to update memory somehow, right? So these are two options. So you can update other caches or you can invalidate other caches. The question is, whose responsibility is this, right? Should the programmer be responsible for this? I'm not going to go into a lot of detail on this one, but the key question here is, can the programmer ensure coherence if caches are invisible to the software? And the answer should be immediately no over here, right? Because if the hardware does this caching internally, and the programmer has no idea that the hardware is doing the caching, programmer cannot prevent this problem, right? Because the programmer doesn't even know that location X is in some other processor's cache. Now you could try and give some options to the programmer. These are some options that don't work, actually. For example, flush local, the programmer can basically insert this instruction saying, flush the cache block containing address A from this processor's local cache. It doesn't work. Flush global, flush or invalidate, flush meaning invalidate basically, get rid of the block, the cache block containing address A from all other processors' caches. Or you could do actually flush a particular block from your cache. So flush global is a bit more interesting actually, although it doesn't work if you do it at the programmer level. So basically, what you could say is, before the programmer does a store, it inserts this flush global instruction. And what that instruction does is, it basically goes through all of the caches and invalidates block that's containing, block with address X, right? Now that's good. You got rid of all of the other blocks. And then you do the store. Now the problem is, this is not good enough because after you've done flush global and before you do the store, somebody else may have a load inside the memory system that's loading the old value, right? Because you haven't updated the value yet. You flushed them from the caches, that's good, but you didn't really flush all of the requests. And actually another request may come in between these two instructions because it's completely asynchronous, right? This thread is executing this piece of code, this thread is doing a load. And this load may come in between the flush global and the store instruction over here. And then you have a problem, basically. So it's very difficult to solve this problem with instructions at the programmer level. Now there are some solutions that use the virtual memory system that we're going to talk about. So what you could potentially do is actually say whenever you're accessing a cache block, you basically lock that cache block. There could be an instruction that enables you to lock the cache block at some granularity so that no one else can access it. This requires hardware support, of course. That way you can actually ensure this coherence a little bit, but it requires hardware support that's very, very similar to what we're going to describe over here. Okay, so it's very difficult to solve this problem in software, and if you actually don't solve this problem, programming becomes very, very hard. Basically, if you don't solve this problem, if you don't provide cache coherence, you need to make the caches completely visible to the software, like GPUs do partially today, such that the programmer controls what goes into the cache, every cache. Now, if the programmer completely controls what goes into every cache, that's okay, because the programmer hopefully knows what's in every cache, and then they ensure that this problem doesn't happen. That's a very difficult problem. It's not easy to program that way. It's a lot easier to have caches that are completely invisible to the programmer. The programmer doesn't control anything. And the caches magically provide the illusion that you don't run into issues whenever one processor writes to a particular location. That's the idea. So if the programmer actually has to deal with the caches, it says a specific name. It's really not a cache anymore. It's a cache, but it's a programmer-managed cache. This has a specific name. It's called scratchpad memory. Basically, it's a scratchpad memory that's reserved. That's called fast memory. And the programmer knows that it's fast memory. And then programmer manages that fast memory. This is manual management of a cache or fast memory. There are processors that implement it. It's not easy to do. GPUs with their scratchpad memory or shared memory, they actually have that. A lot of embedded systems have scratchpad memory, but people are actually trying to get rid of that as much as possible because it's not easy to manage. So if we don't have that scratchpad memory, then we need some sort of hardware cache coherence. And this is important because this simplifies software's job. And there are many actual ways of designing this cache coherence protocol and optimizing it. I'm not going to go into a lot of detail. I'll give you a very simple protocol. And that simple protocol is basically invalidate all other copies of block A whenever a processor writes to it. So you need to basically satisfy this in hardware. So you need to provide hardware support to be able to do that. How do you do that? I'll give you one example, actually. This is a very simple coherence scheme. Each cache, this is also called a Snoopy bus, Snoopy coherence scheme. Caches snoop or observe each other's write or read operations via a shared bus. And if a processor writes to a block, all other processors invalidate that block in their cache. That's the idea. So to be able to support this, you need to have an interconnect that all the processors are connected to. And they need to follow the same protocol. So this is very quickly, the simple protocol is each cache can be in two states, valid or invalid. And whenever a processor takes an action on a cache block, it broadcasts that information on a shared bus. So, I mean, this actually requires a lot of assumptions over here. But for example, the local processor can basically read the block or write to the block. The interesting part over here is it also sends actions on the bus. So it can basically say, I'm reading the block or I'm writing the block. So for example, this is the perspective of one processor. If it's writing to the block that's valid, it writes to the block stays valid, and then it sends a bus write signal at the same time. And this bus write signal gets broadcast to all of the other processors. Now let's take a look at the block from the perspective of some other processor. If the block is valid, and if it receives a bus write signal, it basically invalidates the block. It says, I received a bus write signal. That means that some other processor is writing to it, so I'm going to get rid of this copy. Basically, set the bit to 0. Set the valid bit to 0. Okay? So I'm not going to go through the state diagram, and I'm not going to hold you responsible for it, but you can think about it, how this operates. But this is very simple. It's not very efficient because it has only two states, valid and invalid. It doesn't even have a dirty bit, right, in this case. It doesn't even have a modified state. How do you actually encode modified state over here? In this case, we don't encode because this is a write-through cache. Remember, write-through cache is whenever you're writing to the cache, you're writing to all of the other levels. And that's not good, as we discussed last time, because if you write to the cache, and if all your writes to the cache go to the other levels, you're wasting a lot of bandwidth. You're basically not exploiting the locality that's present in that cache block whenever you write to it. Right? So people have developed a lot more sophisticated algorithms, not based on just these two states, but multiple states. And this gets more complicated, of course, as we keep adding multiple states. But I'm not going to go through this in detail. Know that this is a problem, and know one high-level solution to the problem. Okay, so let's talk about non-solutions to coherence before we go into solutions a little bit more detail. Basically, I call these non-solutions. Clearly, if you don't provide hardware-based coherence, I don't think you're solving the problem because you're keeping the caches, in this case, keeping the caches coherent is software's responsibility. And this makes clearly the hardware designer's life a lot easier because you don't need to design coherence protocols. And imagine if you're putting 100 cores on a chip and 100 different caches, you need to keep all of them coherent, right? That's not an easy problem. But it makes average programmer's life much harder. So this is really not a good trade-off to make. And actually, people who made this trade-off in real products have figured out this is really not a good trade-off to make in real life. For example, well, I guess I'll finish this and then I'll give you the example. Basically, the key thing is, should the programmer worry about hardware caches to maintain program correctness? And you don't want the programmer to worry about details like that. Because if you're making the programmer worry about that, now the programmer is managing the hardware at a very low level. And also, if you actually need to ensure overhead and ensure coherence in software, if you find a way of doing that by locking, for example, cache blocks, by locking pages, as we will discuss in pages. So there are mechanisms actually in which you could do this, but there's a lot of overhead associated with that because you're controlling it in software, and software takes time to communicate with the hardware. So as I said, people have actually figured out, how many of you know about the Cell processor? IBM Cell, or Sony Cell, or Sony PlayStation? Anybody knows about Sony? Okay, Sony PlayStation people know, okay. So Cell processor was the processor that was actually designed for some of the latest generations of PlayStation. And it's actually there are a lot of innovative ideas. It's a heterogeneous processor, a heterogeneous multi-core. It had 8 cores, and it had one core that manages all those 8 cores. So that one core was different from those 8 cores. So what the designers of this processor assumed was programmers would be brilliant people who could manage the caches. Basically, they said, we're not going to provide cache coherence. These processors will have scratchpad memory or software-managed caches, and there's no support for cache coherence. It's a programmer's job to ensure that 2 processors don't write to the cache block and get wrong results. And it turned out it was very difficult to program this machine, and that's probably why you haven't heard about the Cell processor after that. It was very nice design, but it didn't survive the test of time, even a few years, because, in my opinion, it made the wrong trade-off in terms of where the responsibility of the hardware and the responsibility of the software lies. And this is really critical. If you put too much burden on the programmer, in general, you're going to lose, unless you provide a lot of support for the programmer so that the management overhead is minimal. But in this case, it's also very difficult. So people try to develop a lot of compilers, actually, for the Cell processor, but it's not easy for the compiler to help with this also if you don't have enough hardware support for it. So hardware support for cache coherence is really important. Okay, so the other non-solution to cache coherence is making all caches shared. Basically, all caches are shared between all processors. Clearly, that solves the problem because you don't have the replication problem of a cache block because you don't have private caches, and there's no need for coherence as a result. But if you make all caches shared, all caches essentially become the bottleneck, because the reason you can enable low access latency to a structure is because you can actually have quick interconnect connected to the computation unit next to it. Right? Now, if you actually try to have that cache, the entire cache to be shared between entire processors, then you have a problem, actually. That you have a bandwidth bottleneck because you have a lot of connections going into that memory structure. So it turns out it's very hard to design a scalable system with low latency cache access if you want to have all of the caches shared. Okay. So basically, we need to have a way. So how do you maintain coherence? I'll have only 2 more slides on coherence, maybe 1 more slide, actually. Basically, we need to guarantee that all processors see a consistent state or consistent updates for the same memory location or same cache block. So a write to location A by processor 0 should be seen by P1, and all writes to A should appear in some order. So there are 2 guarantees that you need to provide. Basically, all your updates will propagate to the other cache, and you need to have a consistent order. But I'm not going to go into detail. You can look at the theory, and if you're really interested, you can take the computer architecture course. To be able to do this, you need a global point of serialization for ordering of the stores. Whenever you do a write, you need to have an ordering to that location. And the reason you have the shared bus in the Snoopy bus protocol is all processors are aware of the write that's going on by some other processor, right? That's the point of global ordering in the Snoopy bus protocol. So the basic idea is very simple. A processor or cache broadcasts its write, update to a memory location to all other processors, and another cache that has the location either updates or invalidates its local copy. So this is a high-level idea. So how do you implement is another question underneath. So I've given you one implementation with the cache, Snoopy cache, right? There are two major approaches to this problem, actually. One approach is you have a Snoopy bus. All processors are connected to the bus, and all operations, reads and writes, are broadcast on that shared bus. And everybody knows what's going on. It's serialized. There can be only one operation on the bus at a given time. And whenever you say write to a block that you have in your cache by some other processor, you invalidate that block. Very simple. Now, the problem with this is you may have a shared bus, maybe up to 4 processors, 8 processors, 16 processors, 32 processors. Now, what happens if you want to have 100 processors or 1,000 processors on a single chip? That bus becomes a bottleneck. Multiple reasons why that bus becomes a contention bottleneck, because multiple processors want to access memory and they want to write, but you are serializing each access through that bus. So you cannot actually support multiple transactions on that bus. And you don't want to delay hundreds or thousands of processors this way. The second issue is if you actually design a bus electrically to actually get requests from hundreds or thousands of different links, this becomes electrically not so good. You have a lot of electrical loading on the bus, so you can run the bus only at very small frequencies. So this doesn't scale very well, although it's not a bad approach for a small-scale multiprocessors. So people have developed some other ideas, directory-based cache coherence protocols, which I'm not going to go into. But you can think of this as you have a mediator. You don't have a shared bus that you broadcast requests to, but you go through some indirection. You go through some other mediator that basically says, you basically ask the mediator, I want to write to this block. Can I write to it? Basically, you send a message to somewhere else, and that some other mediator checks if somebody else already is trying to write to that block, right? And that mediator contains all of the information about all of the caches in the system. It basically knows which block is cached in which processor. And whenever a processor is trying to write to a cache block, it mediates. What does it do? It basically says, okay, processor A is trying to write to this cache block. I know that processor B, C, and E have the same cache block. So what I'm going to do is I'm going to tell processors B, C, and E to invalidate the copies. And when they're done, they will tell me they're done invalidating. And then I'm going to tell processor A, you can now write to the cache block. Right? So that's the directory-based. That mediator is called the directory. Whenever you want to write to a cache block, you have to go through it. So this is more scalable because you can actually distribute these mediators across the address space in different parts of the chip, different parts of the system. There doesn't need to be a single interconnect, right? There's no need for a single bus in this case. That mediator can be sitting anywhere in the network, actually. That's good. The problem is latency, right? You have to go through this mediator every single time to be able to write to a cache block. So existing systems, as a result, do both approaches. At the small scale, they do bus-based coherence. At the larger scale, they rely on directories. You have the question?
Yeah, in regards to the Snoopy bus.
Yes.
Do we assume that there is just one bus write or one bus write or one bus read at one, right?
Exactly, yes. That's it.
So is there any issue why not having 2 Snoopy buses and then allowing concurrency again?
Yeah, you could potentially do that, but then you need to partition the address space somehow between those. Yeah, it gets more complicated for sure. Okay, so I'm not going to go into the detail. To learn more, you should really take the graduate computer architecture class. And if you're interested, you can take a look at it. Okay, so we're done with the caches. Now let's talk about virtual memory.